Welcome to the ArgMin channel, the least valuable math videos on the internet. This is the Real Analysis video series, lecture 18 on continuous functions and on Lipschitz continuity. So we actually introduced continuous functions at the end of last lecture, but just so we remember what they mean, what they are, let's define them again. So you have a subset A of Rn, a function f from A to Rm is continuous at A in A. So this is a pointwise sort of definition. If for all epsilon greater than 0, you can find a delta greater than 0, where if x minus a is less than delta, where x is also in that subset, you have that f of x minus f of a is less than epsilon. So an example that we looked at last time and I'm going to reintroduce is if you take the union from 0 to 1 of the open interval of 0 to 1 and you add in 2 to that set, then if you have a constant function, then f is continuous at 2, even though the limit doesn't exist. So this is another definition of continuity. Then a continuous function that you might have seen in compared to a continuous function you might have seen in calculus. And for details of why this is true, just watch the end of the previous video. Okay, so some follow-on definitions to continuous. Let's define these things again. F from A to R M 1. If f is not continuous, I'll just write CTS because it's really long, at A, in that subset A, we say f is, big surprise, discontinuous at A. 2, if f is continuous at A for all points A in the subset A, we say it is continuous on the set A. If A is well understood from the context, then we can just say, we simply say that f is continuous. So the definition above is pointwise continuity, and here we have pointwise discontinuity, and continuity over an entire domain. So continuous at A, whoops, that's not the definition. Continuous on A is the definition, and f, a function being continuous as a whole. For example, if we have a function from R2 to a real number, such as fxy equals x plus y, and we want to prove f is continuous, and that just means continuous on A. Excuse me. And we fix AB. I'll just make it clear what we're doing. That's what we're to do. There's a solution. Let epsilon greater than 0 be given, and choose a delta equals, who knows, we'll figure it out afterwards. Now suppose x, y is in R2, and this holds. So now we have to show that the norm from the distance between fxy and fab is less than epsilon. Let's just rewrite that to be a bit more explicit in what we mean. Plus y minus b squared is less than epsilon. Now if we do fxy minus fab, that is just x plus y minus a plus b. And if you use the triangle inequality, you get x minus a plus y minus b. And that is equal to the square root of x minus a squared, because an absolute value can just be written as the square of a square root, the square root of a square, and y minus b squared under a square root, since you can just do that. And that is less than or equal to x minus a squared plus y minus b squared plus, because if you put more things under the square root and they are non-negative, as squares are, they have to be larger, or at least what they were, not necessarily larger, it could be equal. And that is just less than 2 delta. And we want this to equal epsilon, so we make delta equal epsilon over 2 up there. So now our proof looks like it works. And yeah, so we used the definition of continuity on a set A, so we showed that whenever xy is less than delta away from AB, because of this norm, that their function values are less than epsilon through some algebraic manipulations. Okay, now a special class of continuous functions are what are known as Lipschitz functions, and they're nice in that you can tell how fast they sort of change, and it's useful in a lot of future other areas. Lipschitz function, if you can find a constant m and r such that f of x minus f of y is less than or equal to m x minus y for all x, y in A. And we need m to be greater than or equal to 0 for the inequality to work, because the norm itself is greater than or equal to 0. So for this to ever make sense, m itself has to be non-negative. Not sure where this mark came from. Oh, that's an I. Oh. How do I get rid of that? There we go. Okay. There's more of this definition. The least such m is called the Lipschitz constant of f. Note that every Lipschitz function has a constant, a corresponding constant. Now, if you want to show continuity, you can just do this little trick. So all Lipschitz functions are continuous. If we can sum that up by saying if Lipschitz, then continuous. If we just choose delta equals epsilon over m plus 1, you can work that out yourself, but it will work with every Lipschitz function. Little property of Lipschitz functions, let me just write it out. Basically an extended version of above. Continuous, say CTS on A, and proof. We fix a point A in the subset A. We got an epsilon greater than 0. And as per above, choose delta equals epsilon over m plus 1. Now we suppose that x minus a less than a, that's an epsilon, and that's for an x in a, not outside of it. The norm must then be like such, because from the Lipschitz inequality, and this is from by just substituting, and then that gives us this inequality. And simplifying, we now have that is less than epsilon. Okay, so Lipschitz means continuous, and a nice class of Lipschitz functions are linear transformations, which you might have seen in a linear algebra class. Transformation. I won't go over the details of what they are, but it just means it satisfies the properties of linearity, the important ones being t x plus y equals tx plus ty, and t alpha x is equal to alpha tx, and that's for xy in Rn and alpha as a real number. Just a bit of an aside to refresh your memory. Let's prove that linear transformations are Lipschitz. So let's fix a v in, oops, not curly braces, but round, in Rn. Then you take the norm of that, then you get x1 times the first basis vector, and you get all the way up to xn times the first standard basis vector. And you got, oops, that's a 1, x1 plus xn t en. So we just applied linearity there. We broke up the sum, and then we took the x1s and the xi's out, and that is less than or equal to this using properties of norms. Now if you let m equals the maximum of these, then we have that t of v is less than or equal to m times, if you factor them out, this is continuing from this last line, by the way, so each of these is less than or equal to m, so that's where we got that. And that's less than or equal to mn times the infinity norm, where the infinity norm, say for u, is equal to the maximum ui for all I in 1 to n. So just the largest coordinate, and that is less than or equal to the norm. It's a well-known inequality. Infinity norm is less than or equal to the norm. So now we have for xy and a, tx minus ty is equal to tx minus y is less than or equal to mn times x minus y. So Lipschitz constant is this mn. Okay, some special functions. So say f from R to R is differentiable, and the norm of f prime x is less than or equal to m for the absolute value x in R. Now let a b in R a less than b by the mean value theorem. There should be a c between a and b such that f of b minus f of a over b minus a is equal to f prime c, the derivative of f at c. If you don't remember what the mean value theorem is, it's if you have a curve and a point A and B, that slope between them should be the slope at some tangent line between them. So the C will be here. So now we can conclude. You take the absolute value in both sides, f of A over B minus A, you extend those, is that, which is less than or equal to M times B minus A. So F is Lipschitz. As another example, F from the real numbers to the real numbers, Fx equals ceiling of x. We claim that F is discontinuous at every integer n. So to prove that, we fix an n in the integers and suppose that f is continuous at n. So let epsilon equal 1. There exists a delta greater than 0 such that the absolute value difference between ceilings is less than epsilon when it's less than that delta, or less than that, yeah, I'm mixing things up. So now we just choose an x equal n plus a half. So x minus n is equal to a half if you just do the division there, or the subtraction, and that's less than 1. So we have that n plus a half minus n is less than 1, which implies that n plus 1 minus n, if you do the ceiling on that, and that just gives you 1, and you're saying 1 is less than 1, a contradiction. Okay, and that's it for this lecture. Just to review, we looked at what discontinuous meant. We defined that. We defined continuity on a set. We defined Lipschitz functions and constants. We showed that linear transformations are Lipschitz transformations. Lipschitz, and that differentiable functions our Lipschitz. And we did an example on the ceiling function, discontinuous at the integers. All right, and that's it for this lecture. Thanks. Leave questions in the comments below and like and subscribe if you enjoyed this video.